So now we already have finished our discussion of the black hole type solutions in general theory of relativity. In the remaining part of this lecture, we want to discuss two complicated phenomena. The first one is we want to discuss the behavior of the electromagnetic waves in the vicinity of the black hole. So in particular, we want to consider the following situation, that there is a black hole already created. So this is R equals to Rg. In the very vicinity of this black hole, at the radius R0, which is Rg plus epsilon, there is a creation of a wave packet. There is a wave packet created at this position and climbs out from the gravitational potential and goes to some radius r, which is much greater than R0, which is approximately Rg. So this is a situation, and we want to see what happens with this wave packet. So this wave packet goes according to the following law, because it goes along the radius. So its equation of motion is given by this relation, dt squared minus dr squared 1 minus rg over r. From here, one can find that time which takes for this wave packet to climb from this position to this position, from this position to this position, is equal to r0, integral from r0 to r, dr over 1 minus rg over r. Well, as follows from here. This is just equivalent to r minus r0 plus rg times log r minus rg divided by r0 minus rg. And now we use the fact that r is much greater than r0, hence much greater than rg. This is approximately equal to r plus rg times log of r divided by epsilon. So this establishes a relation between position, radius of at which, how long does it take, how much time does it take for the wave packet to climb from radius r0 to a fixed radius r. As this guy, this wave packet, climbs up the gravitational potential, it performs the work against gravitational force. Hence, its energy is decreasing. Because its energy is decreasing, it is natural to expect that its frequency also is decreasing. How it is decreasing can be seen from the fact that at radius r, the relation between proper time and if one stays stationary at this radius, the relation between proper time and coordinate time is as follows. But this time defines for us the frequency, because omega is proportional to 1 over delta t. So the frequency is just clicking rate. So if this is shorter, this is bigger, frequency is bigger. As a result, we have the following relation, that this guy, omega times g00 of r, omega 1 at g00 r is equal to omega 2 at g00 at r2. So in all, from this relation, what we have is that omega at the radius r, if the initial frequency was omega 0, omega at the radius r is equal to the following relation. But G00 is just Schwarzschild, a component of this component. So as a result, this is approximately equal to omega 0 times epsilon divided by Rg. From here, though, from this relation that this is equal to this, we can find that epsilon, well, from this relation, one can see that epsilon divided by R is approximately equal to the minus exponent T minus R over Rg. As a result, as the wave packet climbs up and time goes by, its frequency behaves according to this law, that omega is approximately equal to omega 0 times square root of R divided by Rg times exponent of minus T minus R over 2Rg. And as a result, the phase of the electromagnetic wave, which is equal to the integral from 0 to t dt prime omega of t prime, behaving like this. It is approximately equal to minus t2 omega 0 times square root of R times Rg times exponent of minus t minus R divided by 2Rg plus constant, irrelevant for further discussion. So this is the behavior of the phase. So what did we obtain? Let me clarify what did we obtain. We basically obtained the following fact, that a solution of Maxwell equation for a wave packet in this gravitational potential is like this. Which letter should I use? I probably should use k times k squared. So this is a solution of this equation. As k goes to 0, this Maxwell, which is wave equation following from Maxwell equation, describing some component either of electromagnetic vector potential or component of electric field or magnetic field. So in this limit, as k goes to 0, we obtain so-called A-canal equation. A-canal equation. So basically, what we did, we found the solution of this equation, in the conditions that we have established, that it started from here and climbed up. So we have obtained this guy. Now, so this is what the meaning of all these manipulations. So now one can see what one obtains. So where we are, we have obtained the following situation, that basically we implicitly have found the solution of this wave equation in the A-canal approximation. A-canal or quasi-classical or geometric optic approximation. So this is the equation appearing in the geometric optic, where instead of waves, wave-like solution of this equation, we obtain straight line, or how you say it, geometric optic solution of this equation. And so this is the behavior under the conditions that we are discussing, that the wave packet started from here and climbed up the potential. So now we want to discuss the spectrum corresponding to this guy, so to the wave packet that we are discussing. So we want to make it Fourier expansion, which is the integral from 0 to infinity over dt times exponent omega times the exponent of this guy minus 2I omega 0 square root of R times Rg times minus T minus R over 2Rg. And this integral is not hard to take, and it is proportional to 2 omega 0 square root of r times rg to the power of 2I omega rg times exponent of minus pi omega rg times gamma function, Euler gamma function minus 2I omega rg. And in this equation, we dropped off all the factors that do not depend on omega. So we kept only the factors depending on omega. So this is the spectrum that we obtained for the wave packet climbing up from the Schwarzschild potential, from the Schwarzschild geometry. And the spectrum then is just square root of the modulus of this function. It is proportional to the minus 2 pi omega rg times the gamma function of minus 2I omega rg squared. And this is approximately, well, this is actually equal to pi over omega rg divided by 1 minus exponent of 4 pi omega rg minus 1. But geometric optic approximation is valid in the limit when omega, when the wavelength of the packet is much less than rg, which means that this is true. So only in this approximation all these manipulations are correct. So this is approximately equal to pi times omega rg times exponent minus 4 pi omega rg. So this all have been obtained in the geometric optic approximation. We nowhere used quantum mechanics anything, so h bar was not present anywhere. But if we restore it there and define that energy is just h bar times omega, then this guy is proportional to the Boltzmann distribution, where T is equal to h bar over 4 pi rg. So this is so-called Hawking temperature. Hawking temperature describing Hawking radiation. Of course, Hawking radiation is much more complicated process. It's quantum mechanical, demands a much deeper study than that what we have done. We just observed that if there is a source of radiation in the vicinity of the horizon, due to the geometry, due to the specific Schwarzschild geometry, this actually exponential factor follows from the specifics of the Schwarzschild geometry. And due to this specifics of the Schwarzschild geometry, this wave packet, as it climbs up from the black hole to infinity, thermalizes. So it behaves as if it is described by the thermal spectrum. Hawking radiation, of course, demands a different derivation. It is due to the change of the ground state of the quantum field theory. So, of course, this is not a proof of the Hawking radiation, but this is a hint why the Hawking radiation should be thermal. If there is something created in the vicinity of the horizon, it becomes thermal in the infinity. So what remains to be said is the following. We want to discuss another theme. We want to complete our lecture with a discussion of another theme.